Hi, everybody. Today's going to be a pretty big day in terms of lesson. What we're going to do is we're going to introduce and go through a completely different way to measure angles. So what I want you to kind of do is hang tight for a little bit today. If today kind of gets confusing in some spots, then make sure you feel free to pause the video or just kind of hang tight for a second and maybe we can kind of consolidate some stuff in the end that's going to help out. So, we're going to take a look at the title for today. We're going to talk about radian measure, and we're going to go through kind of a process to lay some groundwork for us to understand radian measure. So, take a look at question 1. I'd like you to determine the area of the sector of the circle of a radius 10 centimeters if the sector is 30 degrees. So, this would be the sort of thing that I would expect very few people to have background with. Very few people. So don't be alarmed if when you look at that problem, you're really not sure how to tackle it. What the question is asking then is for a circle that has a radius of 10 centimeters, what is the area of a sector? So if I was to now rotate 30 degrees, what is the area of that sector? So if that sector was shaded in, how many centimeters squared would that sector take up? So that's what the question is asking. So if you feel comfortable to give it a shot, then pause the video and jump in and give it a shot. Otherwise, we're going to walk through this one together. So the first thing that we may consider then is what's the area of that full circle? And so hopefully we're good that to calculate the area of a circle, we have the relationship pi r squared. You can then make the substitution that your radius is 10, and we're going to get down to 100 pi centimeters squared. Now, let's leave it as exactly 100 pi. Don't go and substitute in an approximate for pi and calculate it. We want things to be as exact as possible for as long as possible. So that would be the area as if that entire circle was shaded in. We just need that one sector. So maybe what we can look at then is, well, what proportion of the circle is shaded? So if we were to take a look, we do know that that sector was created by an angle of 30 degrees. And if we had rotated the full circle to shade the whole thing in, then we know that a full rotation is 360 degrees. So really what we're looking at then is what proportion is 30 degrees out of a full rotation? And if we were to reduce that, we get down to 1/12. So for us then to calculate the area of that shaded section, what we really need is 1/12 of the whole circle. And so if we were to go through and calculate that, just for ease sake, we would get down to something like 26 centimeters squared. We don't care about rounding rules in terms of that case. So hopefully a way that we can understand how we could go through to calculate the area of a sector. Now let's start to look at different calculations. And so our next problem then, I'd like you to give that a read. Determine the arc length of a sector of a circle. So now we have to come up with arc length. So at the very least, we understand how we can break down a sector. Maybe I start here, and now I have to rotate 140 degrees. Well, that would put me maybe somewhere around there. This angle would then be 140 degrees. The radius of the circle is 20 centimeters. And what this problem is asking you for now is what is the arc length? So, how long is the arc that is created by that rotation? So for us to answer problem 2, we have to come up with the length of that blue arc. So same thing as before. If you're comfortable to jump in and play around, pause the video and jump in. Otherwise, we're going to walk through this together. So notice then that what this is asking for is a length, not an area. So I would need to be able to work my way through, and we should be okay that to calculate the circumference of a full circle, you either have the relationship pi d, or you can use the relationship 2 pi r. They both represent the same thing. It's weird, I tend to just always go with whichever one of those relationships matches the given information. And so since the problem gave me that the radius was 20, I tend to use 2 pi r, since it gave me radius. Clearly doesn't matter, but we get down that that circle has a circumference of 40 pi centimeters. Now, we should be comfortable for why we then want to look up and see, well, how much or what proportion is 140 degrees out of a full rotation? And if we were to reduce that fraction, we could divide top and bottom by 20, and we're going to get down to a 7/18. And so really what this question is asking for then would be for you to come up with an arc length. Now it's a little confusing if you used a capital A, so I'm going to actually write, to come up with that arc length, I would then need 7/18 of my total circumference. And again, we don't really care about rounding in this case. That would get us down to something approximately 49 centimeters. So we've got a little bit of experience then to be able to work through how do we calculate the area of a sector and how do we calculate an arc length. So let's take a look at a little bit of a different situation. Now, this is going to be applicable to what we've covered already today, but it's going to feel a little weird because I've given you no specifics. When you read problem 3, find the measure of the angle to the nearest degree subtended at the center of a circle with radius r by an arc length of r. Now, a couple things that we break down. First off, there are no specifics. What I mean by that is I haven't given you what's the size of the circle, what's the size of the radius, anything like that. Okay. Second part, when you see this language that says subtended at the center of a circle, really all that means is created at the center of a circle. So everything that we've done so far by putting those angles in place have been subtended at the center of a circle. So for us to be able to see on our diagram, what is this problem asking us? What it's saying is, if I'm going to subtend an angle at the center of a circle that has radius r, find the angle if I also have an arc length of r. So for me to be able to do that, that must have been my rotation. And really what you need to come up with then is the measure of theta. Now, we have the ability to do this, and we actually have the ability to do this pretty easily. However, I want to just put down what we've been doing formally so that we can understand really how all of it comes together. For us, we've been using a comparison talking about what a sector angle was compared to a full rotation angle or a full turn angle. So we have always been using some form of comparison or ratio for a sector angle compared to a full rotation or full turn angle. And hopefully we've been good that proportion that we've always been dealing with is the same way that we would proportionally apply the area of a sector compared to the total area, or, as we did in problem 2, the arc length that's created compared to a full circumference. And so that blue starts to look like a formula in a way. It's not really a formula, it's just the relationship. We talk about the part of a circle out of its whole. So whether that's the part of the angle, the sector angle, out of a full turn angle, or whether that's the arc length created out of a full circumference. Now, what we can do though is we can use that relationship to start to kind of fill in the missing pieces. We know that in this instance, we have a sector angle that we're calling theta. And we know that a full turn angle on any circle is 360 degrees. In this specific problem, we've been told that the arc length is r, and we know how to calculate the circumference of a circle. Now, we know that we have two options, that we have pi d and 2 pi r. I'm going to use 2 pi r because the problem gave me the radius. There's me subbing in all the specifics of the problem that's been created. Now what I can do is I can work my way through, simplify, and solve. The problem itself asked to find the measure of the angle. That means that I want to solve for theta. So I'm going to try to get theta all by itself. So that means that I can multiply out my 360 degrees. And then I can simplify that. I notice pretty quickly my r's are going to divide out. We could have seen that in the previous line as well. And I can reduce that fraction down to 180 degrees divided by pi by dividing top and bottom both by 2. For us to work our way through, that's what that angle would equal. Now, I'm not saying that we understand the significance of what we have on the screen right now, but it is very significant. And what I need to do is just break down some key components to it. Okay, first off, using your calculator, go ahead and punch into your calculator 180 divided by pi. Now, I want you to use your pi button on your calculator. Don't go through and sub in an approximate. Let's be as exact as what we could be. And when we do calculate that approximate value, we get down to 57.3 degrees, basically. Now, a couple things. I'm going to argue to you that that number should make sense to us. Like, we understand that that approximate is pretty accurate. I want us to take a look back at our diagram for a second and notice that this radius that's unlabeled could have also been called r. And if you were to take a look at that sector, well, you notice that that sector is kind of like a triangle. I understand it's not a triangle because it has a curved side, but it's kind of a triangle. And if you were to call it a triangle, then all three of those sides would have the same length. And so really, it's close to an equilateral triangle. And what angle is every angle inside of an equilateral triangle? They're all 60 degrees. So, as you work your way through, the 60-degree one that I care about is the one subtended at the center of the circle. Now, we should also be good that if we are to take the opposite side of that angle and curve it, then we're going to have to pinch in these two sides to be able to hit the ends. And so it should make sense then that the angle measurement we found was something a little bit less than 60. And we get that confirmation on, well, it was actually 57 degrees. Okay, the second thing, and this is the significance for us, that we actually created a very meaningful angle. Notice, we didn't put in any specifics. So what we ended up finding in this case is true for any circle. This was not for a circle with a specific radius. So for any circle, if we ever want to find out what angle creates an arc length that is equal to its radius, then what we end up having is approximately 57 degrees. That is a very meaningful property to us. How do we create an arc length based on the size of a circle? It is so meaningful to us that this becomes a new measurement system for angles. And specifically, what we found in that last line in red is what we refer to as 1 radian. So, for us to be able to kind of go through, we know a radian is about 57 degrees. But that's still us thinking in degree mode. And what we want to do is we want to start to transition and put our thinking of angles no longer in degrees, but now into this new measurement called radians. I need you to know that I've actually worked with radians for so long that I think in default in radians. And I have to actually consciously flip myself back into degrees. I don't think we're going to get there. But if we can start to lay the groundwork for where we start to be fluent with radians, where we stop converting it, then you're going to put yourself really ahead of where you need to be. So let's break down this radian idea a little bit more detail. And so if we're going to break down then this new measurement system, Radian Measure, then what we need to do is we need to break down specifically what is 1 radian. And this is the important feature. That 1 radian, as we go through to determine it, is the measure of an angle which is subtended at the center of the circle. Remember, that just means created at the center of the circle, by an arc length equal in length to the radius of the circle. So in this new measurement, when we go to define, well, what is the length or what is the measurement of 1 radian, it's where the arc length equals the radius. Now we need to turn it into a full measurement system. So not just what is 1 radian, but what is radian measure. And so in blue, you'll notice radian measure is the ratio of arc length to radius. Okay, it is the measurement of arc length to radius. And so what we're always doing in radian measure is we're comparing how long is the arc length compared to the radius of the circle that creates it. So for us to work our way through then, I'm not saying that we have a great grasp of what that is yet. We're still building, but we can add in a little bit more detail. And so if you notice, what we have in red is a really common relationship. That is our radian measure relationship. That an angle theta is arc length compared to radius. We have always measured our angles in degrees. And so you'll notice that theta is degrees to us. But what we need to do is we need to convert it into radians. And so we're going to change it into a ratio of arc length to radius. And so you see in green then a short form relationship that an awful lot of people will use, that is theta equals A over R. My angle is arc length over radius, and anytime I calculate arc length over radius, I am calculating radian measure. So for us to be able to kind of walk through something really quickly, let's start to break down a couple key radian measures. Well, the first one that we can examine is I know that a full rotation in degrees is 360 degrees. Okay, and so what does that mean for us then? Well, as an arc length, I know that if I rotate a full 360, then I have a full circumference. And so my circumference is 2 pi r. If that's compared to the radius, then I can see that my radii will divide out. I then get 360 is equal to 2 pi. And that is huge for us. That what I just found, that in degrees, 360 degrees is actually equal to 2 pi radians. So I know then that a full rotation is 2 pi if I'm going to use radian measure. Now, for a lot of us, we can even see one more measurement that we know. Because if I was to divide both sides of that by 2 and fully reduce my equation, then I would get 180 degrees equals pi. And so I just found that in degree measure, 180 degrees is equal to pi radians. So kind of makes sense. If all the way around in a circle is 2 pi, then halfway through that circle, 180 degrees, would be 1 pi. Now, this last line should also not surprise us, because if we remember from radian measure and our investigation on radian measure, we knew that 180 degrees divided by pi is 1 radian. So the only way that a fraction can equal 1 is if the top and the bottom are the same value. And so what we see then is that relationship when we come in here, that 180 degrees does equal pi rads. Okay, let's take that information that we have and now let's really build on it. Radian measure would not be useful to us if we only had it for a few angles. What we need to do now is expand it to every possible angle. So let's really build. So what you see now on your screen is there is our good old unit circle. Now, some people really focus in on a unit circle. Some people really just deal with their special angles as they rotate. So if you don't have in your background a strong focus of something called a unit circle, don't worry. What we're going to do now is we're just going to use all of those arms that are branching off that set of axes to represent our special angles. So we're going to now go through and put on all of our degree measurements as we go around that entire circle. So for instance, if I dealt with a rotation angle, I know that my positive x-axis is 0 or 360 degrees. What I have on here is every multiple of a 30 or a 45 special angle. So this first terminal arm would represent our 30 degrees, the next terminal arm our 45, the next 60. We get to our positive y-axis, which is a 90, and so on. So if you'd like to pause the video, go very quickly around that entire circle and label on all your special angles. Okay, we should be good to continue on. That would be 120, 135, 150. We get to 180, and we just keep going. So for some of us, it might actually be faster to go like, well, I'm going to go another 30 degrees and another 30 degrees and another 30 degrees and so on. And then we can plug in the 45s that are exactly in between my axes. Sorry, let me fix that. And now we've gone around the entire unit circle with all of our special angles and degrees. What I want to do now is I want to take that unit circle and let's get all of those angles, but now in radian measure. So we did walk through the first couple already. We know that this 0 angle is still going to be 0 in radians, or we know that a full rotation is 2 pi. Okay, the other one that we knew was we knew that 180 degrees was equal to pi. And so we have both sides of our x-axis labeled. Well, now we can just do some fraction work and we can work our way around and fill in the rest. I think the next easiest angle for us to deal with is probably a 90-degree angle, because we can see that 90 degrees is going to be half of 180. And so if I was to take half of pi, then I get an angle of pi by 2. Notice that the way that we end up reading that is pi by 2. Quite often the divide is left out. These angles are going to be so common for us, we want to be fast with them. So that's a pi by 2. Okay. I think we could then work our way through the rest. I think the next easiest angle for us is probably a 45-degree angle, because a 45-degree angle is half of a 90-degree angle. And if I'm going to take half of a pi by 2, then I get a pi by 4. Okay, now let's work and fill in the rest of our angles that are in the first quadrant. So we've got a number of different ways that we could arrive at it, but let's go for our 30-degree angle first. I would hope that when we look at 30 degrees and we compare it back to 180 degrees, that we notice to get 30 out of 180, we have to divide by 6. And so I need to take my pi radians and I need to divide it by 6, so I get a pi by 6. Okay, now we need to come up with a 60-degree angle. Well, there's two ways to deal with that. We could look at it and say, and use the exact same reasoning. To take 180, we would have to divide it by 3 to get 60. So I have to take pi and divide it by 3. So I get a pi by 3. However, the alternate way that we could go through is using fractions. I know that a 60-degree angle is just two 30-degree angles. So maybe I say, well, I need to double my pi by 6. And then we can cross reduce and the 2 divides out and we get a pi by 3. Or maybe you take a look at it and you say, yeah, but a 60 is just a 30 plus a 30. So 60 is a pi by 6 plus a pi by 6. And so when we add those together, we get 2 pi by 6, which reduces to a pi by 3. So many different ways to be able to go through and build up. Okay, let's keep moving then. So what we're going to do is we're going to progress into the second quadrant. We need to come up with now the radian measure for 120 degrees. And I think your best way to think about that is to use rotation angles in a way. If you know that a 60-degree angle is pi by 3, then we should be able to come in pretty quick and say, let's double that then, and come in with 2 pi by 3s. Now, we could also go through, though, and use a related acute angle. Now, I'm just going to label something on our graph that to get to 120 degrees, that means that we are 60 degrees short of our x-axis. And a 60-degree angle in radians is a pi by 3. And so I could calculate 120 and name that in radians by trying to take all the way to 180, which is pi, and subtract off my pi by 3. As we begin to use radian measure, that red is quite often going to be the way that you determine what 120 degrees is in radian measure. Now what we're going to do is we're going to take 1 and subtract off a third, and so that finishes with 2/3. You're going to find that to be a very useful way to come up with 135 degrees. So let's keep going around our unit circle. 135 degrees would be all the way to pi and subtract off a 45 degree. Well, a 45 degree is a pi by 4. So if I was going to take 1 and subtract a quarter, then that's going to give me 3/4. And so my angle measurement is 3 pi by 4. What I want you to do is to try to go around the entire unit circle now and fill in all the remaining special angles in radian measure. So pause the video now, see how well we do. Okay, we should be back. So maybe we're a little tentative and we're still building. Maybe we're using this as a check. For us to be able to go through and get 150, I want to think of that as pi minus 30. Well, 30-degree angle is a pi by 6. So if I take 1 minus a 6th, then that gives me 5/6, or 5 pi by 6. Okay, I'm going to stop writing down all that red as we keep going. Because what you'll notice as we move into the third quadrant, for me to get to 210, what I need to do is go to pi and add on a pi by 6. And so if I take 1 and I add on a sixth, then I'm going to get 7/6, or 7 pi by 6. Now to get to 225, I need to go to pi and add on a pi by 4. So 1 plus a 1/4 is a 5/4, 5 pi by 4. For me to get to 240, I now need to go to pi and add on a pi by 3. So 1 add on a third would be 4/3, or 4 pi by 3. For me to get to 270 might be a pretty easy one for us. Because what we need to do is we need to go to pi and then add on another 90 degrees. So add on another pi by 2. So we're going to take 1 plus a half, that's 3/2, 3 pi by 2. And as we move into the fourth quadrant, we're probably going to use related acute angles again. This time for me to get to 300, I notice that I am a pi by 3 short of a full rotation. So I'm actually going to pop in the red one more time. A full rotation would be 2 pi. I have to subtract off a pi by 3 from it. So I'm going to take 2 and subtract a third. That means I need a common denominator of thirds. That means that I need to take 6/3 and subtract off my 1/3. And so we get to a 5 pi by 3. Using that same reasoning, to get to 315, well, 315 would have a related acute angle of pi by 4. So I want to think of my full rotation then, my 2 pi, in quarters. That would be an 8 pi by 4. So if I was to take 8 pi by 4 and subtract off a 1 pi by 4, then I get to 7 pi by 4. And if we were then to move to 330, that would now be a full rotation, but in sixths. So I have a 12 pi by 6, subtract off 1/6, and there's my 11 pi by 6. There is us working around the entire unit circle, now being able to talk about all those angles in radians. So your job is to make sure that we can work our way through and develop what each one of those angles are in radian measure. As you're looking in the first quadrant, I think it's really, really important that we know a full rotation, or 0, is 2 pi, and then we have pi by 2 broken down, and each of those individual special angles are 30, 60, and 45, and we know those ones cold. So for us to be able to work our way through, one way that we can kind of remember a little bit, that pi by 6 is the smallest of those special angles, is that I am taking pi and I am dividing it by the largest value. And so if I divide it by the largest value, then it creates the smallest angle. On the other side of things, when I take pi by 3, I am dividing by the smallest number, and therefore that creates the largest special angle. So, some things for us to consider. Lastly, I want to make sure that we also have a really good sense of what those radian measures actually apply to when we start to break down a length. I know that when we take a look at this now, 5 pi by 6 doesn't really have a whole lot of meaning to us, 4 pi by 3 the same. But if we broke down some key values as we worked our way around, I think that can help. If we just dealt with some approximates, we know that pi is approximately equal to 3.14. So if we were to go through and talk then about what is our half rotation, then we know that to rotate all the way around to our negative x-axis, we've rotated an arc length of 3.14 rads. That then means if we were to break down our other axes, well, if I was to take half of 3.14, then I know that to rotate to a pi by 2, I'm rotating about 1.57 rads. All the way around on our rotation would be 2 pi, or approximately 6.28 rads. And then if we were to go down to our 270 degrees, or 3 pi by 2, that would be like 1.5 pi's, which is about 4.71 rads. If we can kind of keep in mind, at the very least, that pi is going to be 3.14 radians, and so half of that puts us in a 1.57, and all the way around gives us 6.28, then I think that that's going to give us a good basis for understanding some of the uglier answers we're going to work through. So, I've thrown a ton of information at you up to this point. What we want to do is make sure that we're good to work around our unit circle. So what we're also going to need is a way to be able to convert degrees to radians and vice versa. So what I want to do is I want to take a look at A and B, for instance. Those are two angles where we should know what those angles are in the alternate measurement system. But how could we go through if we didn't have that means? Well, the first thing we're going to do is we're going to convert units. And so really what I do to be able to convert units is I actually change my units from one system to the other one using a conversion factor. And so for us, I know that 45 degrees, I'm going to multiply that by a value of 1. Now, it looks weird when you see it as 1, because 1 is not going to allow me to change units. However, if I was to change the form of that 1 into an alternate form of 1, like 2 over 2 is equal to 1, pi over pi is equal to 1, that if I chose a different form of 1, then I would be able to convert those units. And so what I'm going to do is I'm going to choose a form of 1 that contains both degrees and radians. And so we notice that pi and 180 degrees are both equal because that equals 1 radian. And so if I was to multiply 45 by, then I could divide out my 45, and I could reduce that down to a pi by 4. And just a little confirmation, you can look back on your unit circle and see that 45 degrees is in fact equal to pi by 4. We can work our way through B as well, except in B, I'm going to want to use a different form of 1. Now, you might look at that and say, okay, well, why would I want that? Because for me to be able to reduce, I need to divide out my radians. And now I could also cross-reduce. And in fact, I get a little confirmation that pi by 2 is equal to 90 degrees. And so the big takeaway for us after A and B is that if you need to convert, whatever units you want to convert to, put them on top. So if you want to take degrees and change them to radians, then what you want to multiply by is the form of 1 that puts radians on top. If you wanted to take radians, and turn them into degrees, then you want to put degrees on top. And so if we now jumped in and we took a look at C, I gave you a measurement of 4 rads. We need to turn that into degrees. Well, the first thing you'll notice is there is no pi in there, which means that that 4 rads is actually an approximate value. And so what I'm going to do then is I'm going to convert that into an approximate number of degrees. And so in that instance then, if I'm changing it to degrees, then I need to multiply by the form of one that puts degrees on top. And so if I do a quick calculation and I have 4 multiplied by 180 divided by pi, I'm going to get approximately 229.18 degrees. Now, I'm hoping that that kind of makes sense to us in terms of an approximate. That when we think about our general rotation, we know that to rotate all the way around to pi means that we just rotated 3.14 rads. That when we go to pi by 2, the positive, we went to about 1.57 rads. So if I needed to go 4 rads, then I need to rotate 3.14 and a little bit more to get to our 4 rads. And so that would have to put me then in the third quadrant, and we get a little confirmation. Yeah, about 230 degrees would put me down there. So there is a means for us to be able to convert if we're given something a little uglier. So our last problem then, and this is going to be one where we can kind of get an immediate sense of whether we really understand what radians are, or whether we're going to have to kind of work through a means of kind of memorizing them for the short run and then building on that. So give question 2 a read. So we need to come up with the length of the arc of a circle. Now, what I'd like everybody to do is pause this problem and let's work our way through it. Let's see if we can come up with a solution to it. So pause the video now. Okay, maybe we have a solution to it. And the biggest part I want to give you now is you should have an exact answer to this problem. If we really understand what radian measure is, you should have an exact answer, no rounding. Now, I'm going to bet and say that we've got a lot of people who have a rounded figure. Because perhaps you started off with this problem and you said, well, this is kind of like question 2 from the very beginning today. That if I had a circle and it has a radius of 5, I have a rotation that's going to be 2 rads. Well, that means I would have to rotate somewhere in here because I got to be in between 3.14 and like 1.57. So I need then to come up with what is this arc length if this is 2 rads. Then if I end up dealing with that in terms of, well, I know that 2 rads out of a full rotation, so 2 rads out of a full rotation, which was 2 pi, has to be the proportion that I apply to a full circumference, which would be 2 pi r. Then maybe we start to work our way through. We might then go through and see, we could come up with an exact value. Notice your 2 pi's divide out. Now, I'm going to bet and say that we would also have had a bunch of people, though, that would have gone through and said, okay, well, we just did how do we convert? And so maybe what I'm going to do is I'm going to take 2 rads and I'm going to multiply that by 180 over pi to turn that into degrees. And as soon as you do that, you notice you're rounding and you're not exact. I want to come up with a way that we can see this problem and why it truly represents whether we understand radians. The question said, find the length of the arc of a circle with a radius of 5 centimeters and an angle of 2 rads. Well, if I understand what radians are, 1 radian is when my arc length equals my radius. So if I was to take a look at a problem like this, and I'm just going to draw a picture, it would never be a part of your solution. That if I have a radius of 5, then if I rotate 1 rad, that creates an arc length equal to the radius. So if I was going to rotate another 1 rad, then I would have another arc length equal to the radius, another 5. So for me to actually get the answer to this, then my arc length is really just my radius multiplied by my rads. So I think problem 2 highlights for us, do we really understand what radian measure represents? Or is it something that's still pretty abstract to us that we're going to struggle with as we kind of build on a memorization platform? So there's nothing wrong if we don't have it, but what we're going to do is we're going to work towards a deeper understanding. Okay? Big part for us moving forward. Make sure we can break down a unit circle, and we work as hard as we can to make radian measure be as fluent as we can when we think about angles. Okay, your job. Jump in today, get a little bit of practice, make sure we're good to go for the next. Good luck.